Welcome to e-Pathshala for PG course content. We are looking at series of lectures on networks. So, we have been looking at the TCP model, the TCP IP model, and we have been looking at the TCP protocol. So, we are looking at how TCP provides reliable data transfer. So, of the reliable data transfer mechanisms, we have already looked at connection oriented mechanism, sequencing, flow control. So, what we will be looking at today will be on retransmission and congestion control. So, retransmission essentially is to take care of lost or erroneous packets, and congestion control is to take care of the bottleneck at the network. That is when you have too much of data in the network and the network is not able to handle the amount of data that is to be transmitted, then congestion occurs, and we look at how TCP takes care of that as well. Okay. So, let us start with retransmission mechanism. So, how is it that a retransmission, how do you determine when a retransmission is to be done? So, retransmission has to be done only when something is lost or there is an error, in which case you will not get back an acknowledgement. So, lack of acknowledgement becomes the cause for retransmission, and a lack of acknowledgement is used to trigger a timer, which will causes a timer to time out, and once that happens you will retransmit the packet. This is the basic retransmission mechanism that is normally used in any network, and that is what is used in TCP as well. But the main challenge that we have here is how do we actually set this timer value? Okay. So, this is where there are some ingenious mechanisms that are used by TCP. So, let us first look at some retransmission scenarios. So, look at what are the things that we could have. So, normally this is the typical case of a packet lost or an erroneous packet. This the first example here. So, a packet is sent, it is lost. So, what happens is no acknowledgement comes back. So, you time out, and after the timeout the same packet is retransmitted, and you get an acknowledgement for that. Once you get the acknowledgement, you know that the packet is going through, and you continue with your transmission. This is one scenario. Another scenario could be that the packet reaches correctly on the other side, but the acknowledgement is lost. If the acknowledgement is lost, what happens? Again, you have not received the acknowledgement on this side. So, you will time out and you will retransmit the packet. There is a slight complication in this scenario, because on the other side there are two copies of the same packet that are received. Though both were received correctly, you did not receive the acknowledgement, therefore, you ended up doing the retransmission. So, it is actually a retransmission that could have been avoided, but of course, you have to retransmit because you have not got an acknowledgement. So, this is a duplicate packet also the generating scenario also that you will have to handle, take care of. Okay. Third scenario that you have is that you send out a packet and you are receiving the acknowledgement also, only thing that the acknowledgement is delayed, or your timeout has occurred quickly or little earlier than the normal round trip time, in which case you would have timed out and unnecessarily you would have retransmitted the same packet, though everything was actually going fine. Because of delayed acknowledgement or because your timeout, the time that you had for the timeout was inadequate, was less than the actual round trip time, you ended up sending a duplicate packet. Now, both these scenarios, this is obviously a scenario that you want to avoid, right? This right side thing is something that we definitely want to avoid, and the second case also is something that we would like to tackle. Okay. Of course, the first one needs to be anyway handled. Okay. So, how is it that the retransmission mechanism tries to take care of all these three scenarios is what we will see now. So, how long should the sender wait? So, that is the basic question. Okay. If it waits for too short a time, as we saw, you will end up wasting retransmission, you will unnecessarily retransmit. If you wait for too long, then there will be excessive delays when the packets are lost. Okay. So, how do what is it that we should do? So, what TCP does is, it sets the timeout as a function of the round trip time. Okay. So, which means you need to know what is the round trip time. So, once you know what the round trip time is, TCP can use that round trip time and use your timer, the timeout value as a function of that RTT. Okay. So, what is it we do? We expect an ACK to arrive after an RTT. Okay. So, plus you can add an adjustment factor to account for some queuing delays and other things, right. So, that can be your round trip, the estimate that you have for your timeout calculation. Okay. But the next question that comes is, how exactly will the sender know what the RTT is? How do I get this round trip time? Because the round trip time itself can vary depending on the characteristics of the network. If the network is not very congested, RTT will be less. If it is very congested, RTT may be high, and so on. Okay. So, how do I actually get an estimate of the RTT? I get it by watching the ACKs. Okay. So, you actually have to measure the RTTs, that is what TCP does. Okay. So, what the original algorithm for retransmission, okay, that was used in TCP does is the following. So, you actually measure the sample RTT for every segment ACK pair. That is, when you send out a segment and you get an ACK for that, you have a timestamp at a time for the time at which it was sent and the time at which the acknowledgement is received. calculate the time between these two, and that becomes your sample RTT. Okay. You do not use only one sample RTT, but you keep taking samples and you take a weighted average of the different samples that you receive. Okay. That becomes your estimated round trip time. Okay. So, how is the weighted average calculated? Basically what you do is you have your earlier value of estimated RTT. So, that is weighted by a factor of alpha, plus you take the current sample, which is your sample RTT, you weight it by a factor of beta. So, obviously your alpha plus beta will be equal to 1. Now, normally we choose an value of alpha between 0.8 and 0.9 and beta value is chosen to be between 0.1 and 0.2. So, which means we give a slightly higher value to the estimated RTT and a lower weight factor to the sample RTT. This is basically done because we do not want slight variations in the sample RTT to totally offset your estimated RTT. Okay. Suppose for instance, one particular packet alone was delayed for a long time. You do not want that one single packet's RTT to upset your entire estimated RTT calculation. Okay. So, beta is normally given a smaller value, alpha is given a higher value. Okay. And the timeout value is said to be twice the estimated RTT. So, this is basically how the original timeout factor was set. Okay. So, based on this you will see that this is typically how your actual RTT could vary. This black line indicates your the sample RTTs, okay, this is the sample RTTs, and this pink line here is the estimated RTT. So, you can see that the estimated RTT will kind of try to track this sample RTT that you have. Okay. But there is a flaw in this approach. So, look at what can happen in these two scenarios. So, let us say for instance, this was your original transmission, okay, and there was some timeout that happened and therefore, you ended up retransmitting the data. Okay. You got back an acknowledgement. Okay. Let us assume that this acknowledgement was for the retransmitted packet and not for the original packet. Okay. But since you did not get an acknowledgement for the original transmission, your sample RTT calculation may think that this was the time at which the ACK is received and this was the original transmission time. So, this entire time, this big duration that you have here, this is what it will treat as the sample RTT, okay, this time minus this time. Okay. But actually sample RTT should have been this time minus this time, there is a time at which the retransmission was done. Okay. This is one scenario, or it could be the other way around, right, that is you actually transmitted an original packet for which you get back an acknowledgement, but before you got that acknowledgement you actually retransmitted the packet. Now, if you assume that this acknowledgement was actually for the retransmitted packet, then you will think that the sample RTT is only so much, okay, but actually this sample RTT in this case, the actual round trip time between the original transmission is actually between the original transmission and this ACK. So, it should have been this, but you will measure it as this. In this case, in the first case, it should have been only this, but you are measuring it as a larger value. Okay. So, when you have these duplicate transmissions, okay, and a retransmission takes place, we have this ambiguity of not knowing if an acknowledgement is received, whether the acknowledgement is for the original transmission or whether the acknowledgement is for the retransmitted packet. Okay. So, this is a problem which can offset, which can totally throw off your sample RTT calculation, okay, and that can cause a change in your estimated RTT. So, what do we do to take care of this? Now, if you actually look at it deeply, so what is this ACK actually acknowledging for us? It does not really acknowledge a transmission, but it only acknowledges the receipt of the data, right. So, what is it that we actually need? So, in the first case for instance, if you consider the retransmission of the lost packet, if you assume that the ACK goes with the first transmission, the sample RTT becomes too large. If you assume that the ACK goes with the second transmission, the sample RTT comes out to be too small, right. So, this is what we have. So, a solution for this was given by Kahn and Partridge. Okay. So, they came up a very simple solution. All they said was this, they said you collect the samples for segments which are sent only one time, that is if you do a retransmission, in those cases do not consider those samples for calculating your estimated RTT. Okay, this is a very simple approach that they give. So, obviously automatically you can see that in the sample RTT calculation, this error that we have, right, both these things are done away with, because in both these cases we have done a retransmission. So, we do not take into account this particular sample RTT at all for the calculation. Okay. But since a retransmission has occurred, there is something happening with respect to the round trip times, right, or with respect to the network, some congestion is there or something is happening in the network. So, what we do in these cases is that you just double the timeout after each retransmission. Okay. So, this was a suggestion that was given by Kahn and Partridge. Okay. So, this was an algorithm that was introduced into the TCP model once they started facing these kind of problems. Again, even in this approach there was another limitation that was noticed. the limitation basically is that this calculation that we are talking about, the simple averaging weighted average of estimated RTT calculation, does not take the variance in the RTT into account. Okay. That is, if your variance from the sample RTT is very small, okay, if the variance is small, then the estimated RTT is quite accurate. Okay. But if the variance is large, then the estimate is not all that good. So, what do we do in this case? So, instead of only calculating the average value, it would be good to also take into account the variance. So, this is what was proposed by Jacobson and Karels, and this is the Jacobson and Karels algorithm which is used currently in the TCP implementations today. So, what we do here is you consider the difference, that is the sample RTT minus the estimated RTT, see how much it is deviating, right. So, you take an average of this deviation and you boost your estimate of the RTT by this factor, okay, depending on whether you have too high a variation or too small a variation. Okay. So, let us look at how that is done. Okay. So, these are the fresh set of calculations that are proposed to take into account the deviation factor as well. Okay. So, what do we do here? First thing is you calculate this difference between the sample RTT minus the estimated RTT. Okay. So, that we call as the difference factor. Now, your estimated RTT again is calculated the same manner, which is estimated RTT plus delta into this difference. Okay. You can see that it is very much similar to the normal estimated RTT calculation that we have. It is just weighted now by a factor of delta and 1 minus delta. Okay. So, now we calculate the average of this difference, right. So, how is that calculated? Deviation is calculated as previous deviation value that you have plus delta into mod of difference minus deviation. Okay. This difference is the value that you are calculating now. So, it could be higher than sample RTT, could be higher than estimated RTT, in which case it would be positive value, or it could be less than your estimated RTT, in which case it will be a negative value. So, we take the mod of this difference and see how much this mod is varies from the deviation. So, that factor is weighted by a value of delta, okay, and you calculate your deviation based on this. So, now your deviation factor that you have here is an estimate of the variance that you have from the estimated RTT value. So, how much your sample RTTs are varying from this mean. So, that variance from the mean is what you have in this factor. So, now what we do is the timeout value is set based on both these factors, that is both on the estimated RTT and the deviation factor. So, timeout is set as some mu into estimated RTT plus some phi into dev. So, this mu is normally set to a value of 1 and phi is normally set to a value of 4. Okay. So, these are values that have been determined empirically, okay, by means of running various experiments on the network, and they found that these are the values which quite closely track the estimated RTT and the timeout values. Okay. So, the delta factor as such, we know that always will be a value will be between 0 and 1. Okay. So, you can see that with this calculation, if there is not too much of deviation, okay, then what will happen, this deviation value will be small, in which case your timeout value will be close to the estimated RTT, which makes sense. But if your deviation is large, then you will see that because you are multiplying this deviation by a factor of phi and adding it to the estimated RTT, your timeout value will become larger. So, you can see that the timeout kind of adaptively changes depending on whether you have a deviation or not. Okay. So, this is how Jacobson-Karels algorithm takes care of both deviation and the mean value. Okay. So, this is what is currently used in the TCP/IP implementations, and you will see that in the implementation we normally, since there are a lot of multiplications and divisions that need to be carried out, these factors that you are multiplying them up by are typically powers of 2. So, that you can do an implementation of this multiplication operation using just a shift operation. Remember that multiplying by 4 is equivalent to shifting left by 2 bits. So, those are the kind of optimizations that are done when the calculations are actually carried out. Okay. So, this is basically how the adaptive retransmission mechanism of TCP works. Okay. So, next thing that we can also look at is another addition that can be done in this retransmission mechanism. So, as we saw, this normally a timeout based retransmission is inefficient. We will take a look example of what normally happens in these cases. See, what is that you normally do, since it is a sliding window kind of a protocol. So, what you would normally do is that when retransmission happens, so from the packet that was lost, you will start transmitting all the packets from that onwards. Okay. That is, for instance, so let us say I transmitted packets 0 and packet 1 and packet 2. Okay. Now, 0 and 1 reached correctly, but it was only packet 2 which was lost, and then I have transmitted also packet 3 after that. Okay. But packet 2 was lost, 3 has reached correctly onto the other side. All right. Now, I will receive back acknowledgements for packet 0 and packet 1, okay, and I may also, and when I receive these acknowledgement, I will end up moving my window and I will send additional 2 packets. But when these packets are sent, they will send back acknowledgements, but which packet will they acknowledge? They will only acknowledge packet 1 because packet 2 has been lost. And remember, our acknowledgements are normally cumulative. TCP's acknowledgements are cumulative, so it will only acknowledge up to the packet that has been received in order. So, in order I have received only up to packet 1. So, I have not received this packet. So, what will happen is eventually, though you have transmitted these 2 packets, now you will time out, okay, because you did not receive the acknowledgement for this, and when this packet 2 times out, starting from packet 2, you will end up transmitting packet 2, packet 3, packet 4 and packet 5, of which actually 3, 4 and 5 have reached the other side correctly, okay, only 2 needs to be retransmitted, but we have done an additional retransmission, okay, because of this timeout and because of this mechanism. So, how can this inefficiency be removed? So, if you look at what is actually happening, that is a quick solution that can be used. Okay. So, what is actually happening here? Packet n might have been lost, in this case packet 2, but you are seeing that packets n plus 1, n plus 2 etc. are all going through, okay, which means the receiver is continuing to get packets and it is sending you acknowledgements saying that it is still waiting for the nth packet. That is, it is sending you what are called as repeated acknowledgements or duplicate acknowledgements. So, these duplicate acknowledgements that we received, right, these duplicate acknowledgements saying that I have received ACK 1, I have received to packet 1, this duplicate acknowledgement is an indication for us that the network actually is sending packets and later packets have been received. So, what you can do is, when you receive a certain number of such duplicate acknowledgements, you can take it as an indication or as a hint that a particular packet, the nth packet actually must have been lost, but other packets are going through, and do that retransmission earlier. That is, you do not have to wait until the timeout occurs, but even as you start, when you receive a certain number of duplicate acknowledgements, you can treat that as a trigger and retransmit your packet. So, normally what TCP does is, it uses a 3 duplicate ACKs as the trigger for doing a retransmission. In this case, what would have happened? So, I received this acknowledgement. If I had received 2 other acknowledgements before this timeout happened, I could have retransmitted the packet 2 without waiting for the timeout to occur. So, this is another fast retransmit mechanism which is used in TCP in order to make your retransmissions better. Okay. Now, how effectively will this retransmit mechanism actually work? Okay. So, when does it actually work really well? So, this will work very well when you have very long data transfers, okay, which means there is a high likelihood of many packets in flight. So, you can expect that if just one packet is lost, you will receive a few duplicate ACKs, and because of the duplicate ACKs, you will be able to do a faster retransmit. And it will also work well only when your window size is large, because if your window size is not large, your window size itself will restrict the amount of data that can be transmitted. Okay. And it works better when you have low burstiness in packet losses. That is, you do not have bursts of packets being lost, it is just 1 or 2 packets that are likely to be lost at any given point of time. Okay. So, in these cases, this fast retransmit strategy will work well. But this is not very effective for web kind of traffic, because normally what happens is that in web traffic, most of the web transfers are short, okay, maybe like 10 packets or so, because you will have short HTML files, small images and so on. So, in these cases there may not be too many packets in flight. So, in which case your fast retransmit mechanism is hardly likely to really kick in and start making your retransmissions faster. Okay. So, in these cases it would normally cause the user to reload the browser or the tab more often, and it may end up, you may end up not having very fast transfers. Okay. So, but when you have large amount of data transfers being done, this kind of a mechanism is pretty useful. Okay. Next, we will take a look at the congestion control mechanism that is employed in TCP. Okay. So, now remember, the congestion normally is a phenomenon of the network, right. It is network which gets congested, and it is normally expected that the network should handle congestion, but TCP, which runs on top of IP, does not have that luxury, because IP does not do congestion control. So, TCP, in order to provide reliable data delivery, also tries to handle the congestion in the network. So, let us look at how TCP does that. Okay. So, what TCP does is, it first of all has to identify that congestion has occurred in the network. Now, it has no direct mechanism of identifying that. So, it has to get some kind of an implicit feedback from the network. So, let us look at what are the ideas that TCP uses. So, what TCP does is, it assumes that the IP network is a best effort network, okay, and it has some particular capacity at any given point of time. Okay. and what each TCP source will try to do is it will try to determine what is the network capacity for itself, okay. And it does it by using some kind of an implicit feedback. What is the implicit feedback? Remember, the only feedback that we have is the acknowledgement. So, the same acknowledgements are used as a feedback about congestion as well. So, what has been found out in the current networking scenario is that most of the time when you have a lack of acknowledgements, that is you do not have acknowledgements coming back, it is mostly because of congestion in the network and not because of actually an erroneous packet which has caused the receiving end to drop the packet or something like that, okay. So, most of the lack of acknowledgements have been found to be only because of congestion in the network. So, what TCP therefore assumes is that if there is no acknowledgement, then it must be because of congestion, and immediately it starts taking some congestion control steps, okay. So, but in order to do all these things, TCP now needs to know what is the available capacity in the network, okay. That is the first thing it has to determine, okay. And once it has determined the available capacity, it will have to adjust to those changes. That is, if there is more amount of capacity available, it can send more data. If it is less capacity available, it will have to reduce the amount of data that needs to be sent, okay. So, how does TCP basically adaptively take care of these things, okay. So, we will see that TCP uses two techniques broadly. One is called as a slow start mechanism and another called the additive increase multiplicative decrease mechanisms. So, we will take a look at these two mechanisms now. Okay. So, the first thing that we look at is the additive increase multiplicative decrease technique. So, the idea here is that you want to adjust to changes in the available capacity, okay. So, to do this, what TCP does is it introduces a new variable called the connection window or the congestion window, okay. Per connection, that is for every TCP connection that you have, it maintains a variable called the congestion window, okay. Just as you have an advertised window, now we also have something called a congestion window. Now, this congestion window is not something which is sent by anybody else, but it is maintained by TCP, right, and it is adjusted based on its view of the congestion that is there in the network, okay. Let us see how that is done, okay. So, what you do is this congestion window is something which is used as an indication of how much data can be sent, so that the data will get through without congestion, okay. So, so what we actually do is before you calculate the effective window size, right, you calculate what is called as a maximum window size. Now, what is the maximum window size? It is the minimum of either your congestion window or the advertised window. Remember, your advertised window is what comes from the receiver side through your for the flow control mechanism. So, let us say advertised window was 800 bytes, but congestion window is 600 bytes. So, then the maximum window size that you use for your effective window calculation will be minimum of these two, which means it will be 600 bytes. So, your more than your flow control, your congestion control is determining how much of data can be transmitted. So, what we do by this particular term, finding the minimum of these two, is that you are determining whether it is congestion that is now controlling the amount of data to be transmitted, or whether it is the flow control that is determining the amount of data to be transmitted. If your congestion value was larger and the advertised window value was small, then you will take that value as the maximum window size, okay. And then for your effective window size, you calculate it as this maximum window size minus the last byte sent minus last byte acknowledged. Now, if you remember from the way flow control is done, this is, you will keep track of how many bytes have not yet been acknowledged and reduce that amount of bytes from the actual window size that is advertised, right. So, that is what we do here as well, and that will give us the effective window size, and that will determine how many more bytes can be transmitted into the network, okay. So, now what we do is you will increase this congestion window when the congestion goes down, and you will decrease the congestion window when the congestion goes up. That is the idea that we want to use. So, we have got one variable called the congestion window, which we will increase when the congestion goes down, and which will decrease when the congestion goes up, okay. So, this is what we do. Now, the question is, how do I know whether congestion is there or not, right. So, that is where we come back to. So, the question, as I said, is how do I know it is congested or not? The answer, of course, is again lack of acknowledgement. Lack of acknowledgement essentially means that a timeout will occur. So, the moment a timeout occurs, okay, the timeout is an indication that a packet was lost, and TCP assumes that lost packet must have been only because of congestion. So, a lost packet implies congestion. So, the moment a timeout occurs, then you start reducing your congestion window, because it is an indication of congestion. So, how much do I decrease it by? Okay. So, this is basically where the additive increase multiplicative decrease algorithm comes in, which is called as AIMD. So, what we do here is, whenever you have to reduce the window size, okay, you will divide the congestion window by 2, okay, this is why it is called as a multiplicative decrease. And when you find that packets are going through, that is that there is that you are getting back acknowledgements in time, then you will increment the congestion window by 1 packet per RTT. That is, you can see what is happening here. So, let us say I sent out, let me assume that you started off with a congestion window size of 1. So, I will send only 1 packet into the network. Now, when I get an acknowledgement for that within 1 RTT, right. So, 1 RTT. So, before a timeout occurs, I have got an acknowledgement. Now, this is an indication for me that things are going fine. So, I will increase now the congestion window by 1 packet. So, now now I can send 2 packets into the network. Now, when I get these 2 packets back, the acknowledgement for these 2 packets back, now I increase the congestion window by 1 more values, okay. So, which now the congestion window becomes 3. So, this is called as the linear increase phase or the additive increase phase. But if an acknowledgement is not received and a timeout occurs, what I will immediately do is I will reduce the congestion value, the congestion window value by a factor of 2. So, for instance, let us say for here we have 4 packets have come in. Now, I sent 8 packets to the network. I am sent out 5 packets to the network. Because I am doing an additive increase, I would have sent out 5 packets. But out of these 5 packets, if the 5 packets do not reach the other side and a timeout occurred, now my window size will become 5 divided by 2, it will become 2.5 or it will become 2. Okay. So, in practice what we actually do is, it is not done in terms of 1 packet as such, but it is done in terms of the number of bytes that are actually sent. Okay. So, the increment is actually calculated based on the maximum segment size into maximum segment size divided by the congestion window, and then the congestion window is incremented by this value that you are calculating here. This increment is calculated as a fraction of the maximum segment size, and that amount of thing is added to the congestion window. Okay. This is basically how the AIMD algorithm works. Okay. So, this is so you can see how this behavior will look like. So, you can see that it will have some kind of a sawtooth behavior, that is, you have an additive increase phase where you keep increasing linearly, and then suddenly there is a drop, right. Once you have a packet loss, immediately your window size, what I am showing here on the y axis is the congestion window size. So, the congestion window size will drop immediately, and then again you will see that as packets are transmitted in the network, you reduce the amount of packets. So, it will start going through, again when congestion occurs, again it will drop. So, you will see this sawtooth kind of a behavior of the amount of data that is transmitted by TCP, because it takes into account the congestion factor. Okay. Now, initially we said that we will start with the congestion window size of 1, okay, that is what we said we will do. But when you actually start off in the network, your advertised window, you would have received some advertised window from the receiver side, and ideally you would like to transmit that many number of bytes into the network. Okay. If you have that capacity, you can actually transmit that amount of data into the network, but we have no idea of how much of congestion is actually there in the network. So, what we do is, initially when you start off, you get a little aggressive. Okay. So, what we do in this case is that initially when you start a connection, when you send 1 packet to the network, you start with the congestion window size of 1 and you get back an acknowledgement, you can send 2 packets to the network, that is, you will double the amount of data that is being sent into the network. So, when you double the amount of data sent to the network, so now my congestion window size becomes 2. When I get the acknowledgement for both these packets, again I will double it and my congestion window size becomes 4. Again when I get acknowledgement for these 4 packets, I will double it again, and now the congestion window size will become 8. So, you can see that in the slow start phase, this is an attempt to determine your initial capacity of the network. So, you kind of go a little aggressive, okay, but you call it a slow start because it is much slower than directly sending an advertised window amount of packets. Okay. So, when you start a connection, you do this kind of a doubling, and once you hit congestion, obviously you will again move off into the additive increase, multiplicative decrease phase, and then from there on you will use a linear increase and a multiplicative decrease depending on whether congestion occurs or not. Okay. So, this combination of slow start and your AIMD is what we use. So, with slow start, you can see how the behavior of the amount of data being sent to the network will be like. Okay. So, you can see that actually slow start is used in 2 different cases. Okay. One is, of course, I said when you first start a connection. It is also used when your connection goes dead waiting for a timeout to occur. So, sometimes you would have transmitted a lot of packets in the network, but you do not there is no activity in the network, and so you time out and you end up retransmitting. So, during this time when you are waiting for some for the timeout, since you have no idea of what has actually happened in the network, in those cases also we will start with the same slow start mechanism. So, you start off again with a window size of 1, quickly ramp up to a particular value and then you can go forward from there. Okay. So, in these cases we also make use of a congestion threshold mechanism. This congestion threshold is normally set to half of the previous congestion window size. So, up to this congestion threshold we will use slow start, and from there on we use a linear increase multiplicative decrease mechanism. So, combination of the slow start and AIMD is what is used in the in TCP for the doing the congestion control. Okay. In addition to these two basic techniques, that is the slow start and fast and the AIMD, TCP also has brought in a few other techniques. Okay. One is called as the fast retransmit mechanism and the fast recovery, which are also useful for handling the congestion mechanism. Now, we have already looked at the fast retransmit technique when we talked about the retransmission schemes, right. So, we said that if I get n number of duplicate acknowledgements or 3 duplicate acts, I will treat that as an indication for a faster retransmit and I can transmit the packet. So, in this, if you look at this example, say packet number 1 and 2 have gone to the other side, 3 is lost. I have sent 4, 5, 6 after that, for which I get back 3 acknowledgements. So, when I get these 3 duplicate acknowledgements indicating that packet number, so remember all these 3 packets will say act 2, act 2, act 2, which indicates that that 2 has not been received, but 3, 4, 5 have received. So, now you retransmit packet 3 and you will get back an acknowledgement for 6 because already these have been received. So, then you can continue with your transmission from packet 6 onwards. Okay. So, this fast retransmit is something which is used along with the congestion control mechanism, plus there is also a fast recovery mechanism that is used. Here again it basically tries to reduce the slow start phase, okay, that we normally have whenever we have this timeout that we talked about. So, what you do in this case is that to do a fast recovery, you will skip the slow start phase and go directly to half the last successful congestion window. So, you keep track of a threshold that you had, okay. So, whatever was your last successful congestion window, half of that value you start off with, so which is what you will see happening over here, okay, and from there onwards you do a linear increase multiplicative decrease, okay. And with this mechanism you can see that since you will be able to recover faster and reduce the amount of delays that are there in the network because of the congestion control that is actually coming into place. So, remember that because we are doing congestion control, there is again a certain amount of decrease in the performance. So, these techniques like fast retransmit and fast recovery, they try to improve performance to kind of offset the problems that we would have otherwise. Okay. So, this is basically what happens. So, combinations of these are what are currently used in the current versions of TCP. Okay. So, we will take a look at some of those versions later, but this is typically what we have in terms of the basic mechanisms of TCP for adaptive flow control and as well as for congestion control. So, to summarize, so we have looked at 2 important techniques of TCP today. One is the retransmission strategy. So, we looked at how the round trip time is estimated and how the retransmission is done based on that. And we have also looked at the congestion control mechanisms, slow start and the additive increase multiplicative decrease mechanisms, and how fast retransmit and fast recovery are also additional mechanisms that are used. Thank you.